So we'd previously talked about how to find solutions to a constant coefficient linear differential equation when the roots of the characteristic polynomial are real. And recently we have now seen how to deal with complex roots. So now let's summarize all together what is our method for writing down solutions to a homogeneous constant coefficient linear differential equation with real coefficients, and get a theorem that we can then use henceforth. So here it is, this differential equation. Write down its characteristic polynomial, find the roots, and there should be n roots if this is an nth order differential equation. From these roots, we form solutions by the following process. For the real roots, look at the multiplicity and write down these solutions. Right, so we have these are the sort of obvious and free solutions, and we have a theorem from the recent lecture recording showing that adding extra factors of x up to 1 less than the multiplicity also yields solutions. And we'll prove that result at a later time. For the complex roots, don't take them one at a time. Take complex conjugate pairs of roots. So don't think of this as just a plus bi. Think of the pair, a plus bi and a minus bi. This pair of roots gives us this pair of solutions, as we previously discussed. Two roots gives us two solutions, so the arithmetic is fine. Furthermore, if there's a multiplicity, then again, extra factors of x all the way up to 1 less than the multiplicity. So if you write down solutions in this way, this theorem tells us that that list of functions is independent, and furthermore, that list of functions is a fundamental set of solutions. You can use this worry-free henceforth for all real coefficient, constant coefficient linear differential equations, homogeneous. Okay. All right. So let's see an example. Here we go. Constant coefficient linear differential equation. Note that all these coefficients are indeed real. And let's use the previous theorem. Write down the characteristic polynomial. There it is. Factor the characteristic polynomial. Now, I skipped some algebra here. There's some doing to be done there. Right? You have to go through and find a rational root and write down the corresponding factor and polynomial division and quadratic equation, etc. So there's some work to be done. I encourage students to do this. Make sure that you actually can factor that polynomial. This is susceptible to the methods that we know in this course. Having done that factoring, we see what the roots are. Here are the 3 roots, and following the theorem on the previous page, here then is our fundamental set of solutions. Okay, so specifically note that this root of minus 1 shows up there. This pair, this conjugate pair of complex roots, the 1 shared there, shows up there and there, and the 1 that's being multiplied by I and minus I shows up there and there. Okay. All right, here's another example. This is a 4th order constant coefficient, real constant coefficient linear differential equation, homogeneous, of course. We'll worry about non-homogeneous later. Here's the characteristic polynomial. That's just a recopy. And here's the factoring, the full factoring of that characteristic polynomial. Now, importantly, this is not something that's susceptible to the techniques that we've talked about in this course. This factoring is harder. So on an exam or any sort of graded assessment, I would have to give you this factoring for something like this. So anyway, don't try to factor this one because our methods aren't appropriate for this. That being said, I can write down what the roots are. We have this as a root, and this is a root. But furthermore, each one of those roots has a multiplicity of 2. Right? So we have a conjugate pair of roots, sure, but we have that conjugate pair of roots with multiplicity 2, and so those are solutions, sure, but so are these. Okay, but we don't like these solutions. Those solutions are complex valued. We don't want complex valued. We had a real differential equation given to us representing presumably, possibly, a real physical system, and we want real solutions to describe the real behavior of this real system. So complex is not desirable. So, per discussions earlier, this conjugate pair is equivalent to this conjugate pair in terms of their span. So we replace those with those. And likewise, these are exactly the same functions, just with an extra factor of x. And so, likewise, with that extra factor of x, these have the same span as these. So, altogether then, here we have not only a fundamental set of solutions, but a real fundamental set of solutions to our real differential equation.